Hello, my name is Dr. Abrahamian, and in this channel I go over problem-solving strategies mainly in math competitions. So this is a problem from the International Math Competition in 2025. This is problem number 8. For an n by n real matrix A, denote A superscript R its counterclockwise 90-degree rotation. For example, they gave us an example of what they do. They take this entry and they put it here. They take this entry, they put it here, etc. So they rotate this 90 degrees counterclockwise. Prove that if A is equal to A to the power of R, which is just the notation for this rotation counterclockwise, then for any eigenvalue, either we have real part of lambda equals 0 or imaginary part of lambda equals 0. Okay, so I'm going to show you how I thought about this problem and how I ended up with a solution. The first thing is I have something similar to this that I have seen before, and I'm going to remind you of those. And that is, if you have a matrix A that is a symmetric matrix, then all of the eigenvalues are real. In fact, and this is only for real matrices, then every eigenvalue is real. In fact, if we have a matrix that is self-adjoint, so A star equals A, which is the same thing as saying A transpose conjugate is the same as A, or it is self-adjoint, then we have this same property. Then we have that eigenvalue is real. And I have also seen something again similar to this, which is if we have a skew symmetric or a skew self-adjoint matrix, then eigenvalues are inside IR. In fact, the imaginary part is real for self-adjoint, and for skew self-adjoint, the real part is 0. Okay, so how do we prove these? And then we'll get to the problem. So the first one, you have A star equals A. So how do we prove that eigenvalues are real? We assume that AV equals lambda V, which means lambda is an eigenvalue. And then we're going to take the transpose conjugate of this, which is V star A star equals lambda bar V star, and star is transpose conjugate. Now, we know that V star and A star and A are the same, so that tells us that V star A is equal to lambda bar V star. So we're going to multiply both sides by V from the right. We get V star AV equals lambda bar V star V. So we can look at this one another way as well. So this side is magnitude of V squared. This is lambda V. So this tells us that lambda magnitude of V squared, because on this side we have V star V, which is magnitude of V squared, is equal to lambda bar norm of V squared. Now norm of V is non-zero because V is a non-zero vector, so that means lambda equals lambda bar, which means lambda is real. So perhaps I can use a similar strategy, but there are two obstacles here. The first one is, what does this even mean? What does this identity mean? And the second one is, we have this or here. How do we turn this or into maybe something that is kind of unifies the two conditions? Let's just start from this one. So this one tells you have a rotation of 90 degrees. How do we relate it to something that is known, like maybe transpose that is used in these two instances for self-adjoint and skew self-adjoint? Well, we need to understand rotation in terms of some form of reflection, because most of these operations that we have are reflections. So for example, if you look at transpose is reflection about the main diagonal. So this is transpose of a matrix. Now we also have these elementary row operations. For example, row swapping. If you reflect along the middle row, then this would be a reflection along this. So we know that if you compose two reflections, you get a rotation. So interestingly, we can understand A superscript R by composition of two reflections. Reflect along the main diagonal and then reflect along the midline or mid row of the matrix. It may not be exactly one row, it could be between the two rows in the middle. Now we can understand each one of these by one operation. The first one, reflection along the main diagonal, is the transpose, and the second one is by multiplying by an elementary matrix. What is that elementary matrix? Elementary matrix is swapping the order of rows. So what does that mean? It means we want something that moves the first row to the last row, the last row to the first row. So it is something like this. This is RE. So in other words, the claim is AR is the same as A transpose. And the reason for that is the composition of two reflections is a rotation. So we were able to turn the problem into EAT equals A. So this is the same as saying A superscript R is the same as A. So that's nice. The second obstacle that we have is about the real part of lambda equals 0 or imaginary part of lambda equals 0. So what does this exactly mean? So one thing we could do is we could write down lambda as a plus bi and see what this mean. What we know is that we have either a is 0 or b is 0. This is the claim. Now, I can understand this one by saying that, well, the product of A times B, the product A times B is 0. So that kind of unifies the two conditions. Now, I thought about this a little bit and I realized that, well, if I square lambda, I get A squared minus B squared plus 2ABI. So this is the same as saying, so if I say AB equals 0, that's the same thing as saying the imaginary part of lambda squared is 0, which is the same as saying lambda squared is in R. So in other words, real part of lambda is 0 or imaginary part of lambda is 0 is the same as saying lambda squared is in R. And just to recall, A transpose is the same as E. Okay, so now I want to see if I can solve the problem given the condition. Now, one thing we know is that if lambda is an eigenvalue of A, then lambda squared is an eigenvalue of A squared, because I know that AV equals lambda V. So this means A squared V equals A times lambda V, which is lambda V. So that is lambda squared V. So lambda squared is an eigenvalue of A squared. So now let's see if we can find something about A squared. So this is what we know. So we're going to take this and evaluate. Let's transpose both sides of this. We get A E transpose equals A transpose. Let's take this and plug it into the condition. So we have E transpose equals A. Now what we know is that E is a reflection. So E squared is the same as identity, and also because it's a unitary matrix, E transpose is identity as well. Why? Because the columns of E are just the standard basis. So if you multiply by E on the right, we get EA and AE are the same, but that doesn't really help. So now I'm going to try to see if I can show something about A squared. Let's evaluate A squared transpose. So what is A squared transpose? Well, A squared transpose is the same as A times A transpose. And if I substitute that here, I get A transpose, A transpose. Now, what is A transpose? I can write down A transpose as EA, because I know from here that A transpose is EA, and then that multiplied by A transpose, which is also EA. So I can commute A and E. That would be E squared, A squared. So this is the same as A squared. So what did we show so far? We showed that A squared is a symmetric matrix. So if A squared is a symmetric matrix, that means all of its eigenvalues are real. And that's exactly what we wanted to prove. And that brings me to the end of this video. I will see you in the next video.